parts that didn't compress, you're going to compress in a different way. Also, there were some, so the original FMM could only handle the matrix vector, the forward operator. But now you have something like the inverse FMM, where you can handle the inverse operation with the FMM form. So not like necessarily creating and storing a matrix. So it still has the low memory footprint feature, but it allows you to use it as a solver now that you can calculate the inverse. And so some of the limitations, like I mentioned, are you need to have numerically low rank of the off-diagonal blocks. Otherwise, if this is completely dense, then this is not a fast method at all. It's just partitioning a dense matrix for no good reason. Okay, and this one requires an analytical form. Like I mentioned in the previous slide, it doesn't necessarily have to be a Green's function. It could be some radial function, but even if you use these kernel independent or black box type methods, you still need the analytical form of the forward operator to start with. So without that, just given a pure dense matrix, black box without any information at all, then you cannot do this kind of geometric variant. So those are the two differences. So in most of my lecture, in the like the past 4 days, I've just been talking about this one, but now you know the relation between, like since this is a linear algebra course, I'm now coming back to a linear algebra representation of what the fast multiple method could be. And I'm trying to carefully give you, the information of when it can be useful and when it won't be useful. Okay, a little bit more on the admissibility and the real reason why this one doesn't compress well for higher dimensions is that if you use this kind of weak admissibility and don't divide the box too much, then you're actually looking at your direct neighbor. So you have white boxes immediately next to you at very small levels, and even at the big levels. So the one that's immediately next to you is trying to be compressed. Here, the boxes that are immediately next to you are actually handled in a dense form, and it sort of skips the immediate neighbor, and then you sort of have only the far boxes being compressed. So you can think of that as only having targets far away from the source. In this case, multiple expansions, and these two are the more algebraic forms, so the matrix way of doing it. They both decay. So this is like the error, and starting from like 10 to 0, minus 2, 10 to the minus 4, 6, 8, 10, 12, 14, and here's where you hit like double precision limitation of like round off. And then this is the ranks. So if you use more ranks to represent, or more terms in the multiple expansion in the multiple case, then of course your answer gets more and more accurate. But it levels off when you hit like 10 to the minus 16. But if it's far enough, then all of them converge. The problem is when you're doing this kind of approximation and you're saying, I want to compress my immediate neighbor. So then you're looking at points that are as close as this one, and then you have these corner elements. So it's not like you're dealing with two concentric circles. This is more like a square. And so this one, the distance from the center of this red point is actually further than the distance from the center to this blue point, for example. And so in that case, the multiple expansion, because the rule for the Taylor expansion that I explained in the first few lectures was that the red point had to be closer than the blue point. That was like the term in the Taylor expansion to be less than 1. If that's larger than 1, then you keep taking the power of a number that's larger than 1, so it's going to slowly diverge. But if you're using singular value decomposition numerically, you can still manage to converge slowly, but still it does the error does slowly get smaller and smaller, but the rank that you need to use is like 150 only to get like 6 or no, a little bit more, 7 significant digits of accuracy. You have to use already 100 terms. So it's like a unreasonable amount of ranks that you have for this off-diagonal block. So basically it's not compressing and you're not saving too much computation or storage by doing this kind of weak admissibility. But so there are advantages. Again, I need to be fair and mention that there are advantages of doing this kind of decomposition. So first of all, if you think of actually factoring this thing, or like inverting or doing low rank updates, the structure of the recursive structure of taking like the inverse of these decomposed blocks is much simpler for this. If you tried to invert in a block nested structure this kind of structure, mathematically it's going to look very, very complicated. And so when you're thinking about inverting this structure, having this weak admissibility is much easier. So if you can come up with a way to compress your direct neighbor efficiently by nesting like a hierarchy, then you can have potentially a much simpler mathematical representation of the inversion structure of the hierarchy of the inversion structure would be much simpler. So so there are advantages and disadvantages to both methods. But so for people who have like already a fast multiple method code, yeah, it's the inversion of the structure is not so much of a problem. So for those people, maybe it's not, they prefer to use this one. So okay, now well, maybe I already mentioned this. So I'm just trying to map the terminology between the two, because if you read a paper that says HSS or H-square matrix, it's going to tell you the same thing in a very different way, and you might get confused. So following the equations that I showed earlier, I'm just trying to map here what the correspondence is between these different namings of the same thing. But so I won't go, like explain one by one. Maybe if you're interested and if you're reading the two papers, you can look at this slide because it'll be online. And then when you're reading the two papers, you can do the comparison. So just to be clear about the naming of what H matrix is and H square matrix is and HSS and HODLR matrices, Ambikasaran and Darv do a nice summary of the low rank structure. So the strong low rank structure or weak low rank structure, or so the strong one is the one that had less division of the boxes. The weak one is the one that had more division of the boxes. So the two pictures that I showed in the previous slide. And so these ones that have like the light purple colors are not dividing the boxes too much, but the dark purple ones are dividing more. The nested basis is something that differentiates between the tree code and FMM, for example. So if you look at this picture, if you remember, this is a direct n-body. Nested basis means this one. Non-nested basis, like no, is this picture. So the tree code has nested, non-nested basis, and the FMM has nested basis. So you can think of these two methods, Hodler and H matrix, as having this kind of shape. If you look at the clustering of the source tree and the not clustered target tree, the not nested target tree. And then you can view HSS and H square as this kind of structure. Of course, this is, this picture is not entirely accurate. It's just a sketch of, sort of the notion of whether it's clustered or not. Of course, these 2 points need to interact directly, so there should be a line that goes from here to here. And there's more, if you want to be accurate, there's more lines that should be drawn here. But this gives you the idea of what these different representations of the matrix versions are. This is another diagram that sort of shows you. This says FMM in this red circle here, just in case you can't see. But this is sort of the categorization of the different names you may encounter when you actually try to study this area. So if you get confused about what means what, then just look at this slide and it'll be very clear what the correspondence is between what is what. And so the FMM, as I've been repeating many times, it takes a geometrical point of view for this hierarchical low rank approximation. HSS you can think as like a numerical linear algebra point of view, because this was developed by numerical linear algebraists like Chandrasekaran and Gu. So they are like the in the field of numerical linear algebra experts. So they come from that viewpoint. H squared matrix is more like an operation. So this comes from the German school. Like Hackbusch was one of the the initial developers of what is now called the H matrix. He used to work on fast multiple methods or panel clustering methods a long time ago, and then so a lot of the people that now work on these hierarchical low rank approximation matrices have in the past worked on fast multiple methods, and so now everyone is trying to generalize what they know to be a very efficient operation and try to extend their field of application. And so you can see the sort of diversity of namings and notions coming from the fact that they were studied from completely different groups that didn't really cite each other initially. But now everyone is citing each other. So the culture is that people from different fields are also aware of each other. And now that people post on their papers on arXiv very frequently, you can immediately see what other people are doing. And it's a good synergy between the different people with different backgrounds. Now we can actually talk and understand with each other and have completely new ideas that were obvious to the other person but not so much to you. So it's an interesting area where everything is intersecting, because n-body people didn't used to talk to like a numerical linear algebra people, and they wouldn't go to the conferences, but now you see like people going to the different conferences, and it's an interesting cross-section of everything that's hierarchical and low rank. And so let's see. Yeah, I still have a little bit of time, so I'm going to explain a bit about what happens inside the kernels. So I've explained that the FMM does these operations P2M, M2M, M2L, L2L, L2P, and P2P using these equations here. And there were different ways to calculate this expensive part, the M2L translation operation. But so there exists the same kind of variety in the matrix form as well. So to do the compression of that M2L translation operator, so these are the geometric ones that I explained earlier. So you can do it with like spherical harmonics, with rotations or plane waves or equivalent charges, and using FFT to calculate them. But now for this side, you can use basically like QR decomposition or LU decomposition methods and some randomized techniques. So these are just pivoted versions of the LU and QR. And ACA and HCA are methods which have lower complexity, but sometimes these methods fail because they don't look at all the elements. So it's not randomized either. So they have like a systematic way of examining the dense matrix and to extract the low rank properties and go like why it's called the cross is because it sort of moves in like a, this way and then this way. So it looks like a cross the way they try to find the next elements to look at. So all of these methods you can think of as like purely algebraic methods. And so they have a lot of memory storage, and they need to store the matrix. And then you could think of these methods as like purely geometric methods. But since I mentioned some techniques like storing the same matrix with the same relative positioning, and just using translational invariance to save the redundant copies. You can also use symmetry. So sometimes a lot of these translation operators are like the same or just switch the sign when you move them 180 degrees. So you can use this kind of rotational symmetry, or like if you change them 90 degrees, they also have like other properties, like they could be like the complex conjugate. So you can use symmetry to further sort of cut the storage. And so you can use all these various techniques to also the algebraic side to reduce the storage. But so also these sampling techniques like the randomized versions, and also you can think of these equivalent charges as some sort of sampling technique too. So there are, it's not just binary. It's not like either you're geometric or algebraic. There's some intermediate points where these methods sort of can be combined. And looking at this kind of roofline model for the different architectures, having control over like the memory and how much you compute is very useful, because you can change where you are in this chart. You don't necessarily have to say FMM is here or FMM is here. FMM and the hybridized FMM H matrix can be anywhere in this chart. It's actually controllable. So if architectures shift towards ones that prefer this direction for some odd reason, then you can have control to go this way as well in this picture. So I'm just showing you that this, when you want to develop such methods, there's a whole catalog to choose from, and you can some are difficult to code and but are very fast, and some are difficult to code but are not very fast. So you need to be careful which ones you choose. So in the hands-on session today, I'll try to use step 8 that we left off last time and add a proper kernel so that you have controllable accuracy over it. I won't necessarily give you these kernels here, but I'll make it possible for you to just swap the different kernels in the code. So maybe step 10 will be a kind of code that you can change just this part and it will still function without changing the rest of the code. So once you have this, I think it's a good sort of final code to take home from this whole coding session, because now it gives you the freedom to experiment with more advanced techniques when the time comes. So okay, this is not really necessary for. Okay, so yep.
Sorry, I think you just mentioned that a randomized SPD is sort of equivalent to the equivalent charge. Is that?
No, it's not equivalent. I'm just saying they can both be thought of as some sort of sampling-based technique. So randomized SVD is a way to sample the dense matrix so that you don't have to do an order n square operation to do the compression. So you can have a much better complexity method for doing the compression phase. And so for the equivalent charges, they are actually taking points instead of so if I want to explain to you what the equivalent charges are, I should show you like this picture here. So these points have, inside the center of the box, you have the multiple expansion. But the equivalent charges actually place the points on the edges of this box. So it's actually outside the box a little bit. And you place like a fake charges there that will reproduce the effect of the multiple at the center. So it's like you're taking and the charges that the strength of those charges that you put there are sort of like sampling. So you can either invert a matrix that corresponds to the strength of so if the forward matrix is calculated from the forward equation, you can actually invert this matrix to calculate the equivalent charges that form that potential. So it's sort of like solving the inverse problem to create the equivalent charges on a given point that you give yourself. And so you're trying to find like charges that will represent your multiple well. And an extension of that in higher dimensions, like the code ASCII will calculate those equivalent charges not by inverting this thing, but it actually, because it's in high dimensions, it takes the actual points in the space that exist in very high dimensions and just uses those as sample points. So in that sense, it's sort of can be thought of as a sampling technique. And yeah, so basically that's why I said these equivalent charges lead to the idea of sampling eventually. So yeah, I'm not saying that this thing and this thing is the same. So yeah, it's.
So for the randomized SVD or truncated SVD, I think that's a sort of a truncate of a low rank approximation.
Yes.
So in the FM side, I think there's some kind of control of degree of the higher expansion.
Yes.
Roughly.
So it's also a truncation. So yeah.
But by introducing the randomized, then how can we correspond that to the truncation of the higher expansion? Because if you truncate that, that's a sort of deterministic.
Yes.
Yeah. So.
Well, so yes, by nature, this method is not determined. I mean, there is some possibility of failure. It's just that it has been proven to, the possibility of this failing is, what was it, like a very, very small number that's so low that your computer is more likely to break before that possibility. So like, computers themselves are not perfect either. They have these things that do memory correction called ECC, but inside the computer is actually failing. If you take it to space, it fails even more. But because the bits flip from the rays coming from space, and so the possibility of this failing is much lower than that happening on Earth. So as long as you're using a computer, the possibility of this failing is negligible compared to the computer failing. So as long as you're using a computer, this should be fine. In the same sense that aiming for a precision that's lower than double precision accuracy is not something you usefully do on a computer. Aiming for a more deterministic method for a higher, lower probability of failure for this one is not really needed at the moment. So yeah, then we can. I wanted to, because I've discussed all these things, here is something that I can explain now, because now you know that the well-separatedness is called admissibility in the matrix form. It's how much you divide the boxes. Because if you divide them more, you have small boxes that are relatively far, which means the well-separatedness is very, very good. In that case, you call it strong admissibility. And the order of expansion is called rank in the matrix form. So there's a correspondence between these two things. Now, you can think of, maybe some of you have heard of HP finite element methods. This is an analogy to HP FEM, and I changed the E to M. So now, H is like a distance-based, so it's like a, H in the finite element methods. It's a criteria of that's associated to the spacing of the approximation. And P is related to the order of, the accuracy that you're expanding to. And then, so in the same way that control of both of these was useful in the finite element community, having control over both of these is useful. And so usually in the geometric fast multiple methods, you don't change H. In the matrix form, the admissibility is determined until, so you sort of keep subdividing the boxes until you get a certain rank. So this H is sort of dynamically determined. So in FMM it's static, and in H matrix it's dynamic. So there's a difference there. But there are methods in the FMM to make, this one. This one has like spatially varying admissibility, even in the geometric FMM. And so what happens is you can either change this or change this to get the specified accuracy, like I mentioned. It's like, well, I was using theta here originally. So I was saying theta to the pth power was the order of the error. But now I'm using H instead, just for this analogy. So you can say H to the pth power is the order of the error. So you can either decrease H or increase P to get a higher accuracy. But now, if you can control the error by changing H spatially to get the target accuracy, then you can have P constant. And you can do the same for the and doing AVX was very fast. And also on GPUs, the width, the SIMD width is like 32. So it's much larger than the 8 of AVX. So we want things to be very aligned. And if you have variable rank, so say P was like 32 here, and it aligned very well with the GPU warp, and it was like 8 here, and it aligned well with the AVX SIMD vector width. But in some other areas, say that it was like 5 or 1 or 2, so if it varied a lot in space, then you wouldn't be able to use the SIMD operations very efficiently. So this is something that becomes a problem only when you're doing very advanced coding. But eventually you want your code to be highly optimized. So when you're thinking about the design of your algorithm, you want to consider the fact that if you can achieve the target accuracy by spatially varying H, like you do in the H matrices, then you can have a constant rank everywhere. So then you can have a very SIMD-friendly code. So if, for example, you can set P to a constant of 32 and worry about the target accuracy by just spatially varying the spacing, the admissibility, or the size of the box, basically. So the size of the box you change, but everywhere you have very good GPU usage because the rank is set to 32 everywhere, for example. And so this kind of HP FMM is actually useful because of the SIMD stuff that's coming. And in the future architectures, like I mentioned, there's going to be more and more speed up by being able to use SIMD. So you need to be aware that there is a way to make it faster for these machines. And yeah, I have, okay, so maybe I'll take a break now because I don't want to run too much over. There's not too much more to explain. I'm just going to cover a few more topics. This one and this one. Yeah, this is my last one. So like 4 more slides. And then we can move to the hands-on. I want you to be able to finish coding the proper FMM with the high order terms by the end of today's hands-on. So I think we will start the hands-on a little bit early. And so, yeah, I'll go and continue the last few slides in the next session in 10 minutes. And then we'll do the hands-on and finish the coding for high order FMM. Okay, thank you.